Hello, I'm Trent, and along with Thomas, and Tim, we were assigned to the voltage station this semester. Here's what I'm going to go over. I'm going to review the SSOC and step response, since Tim has already went over that in his presentation earlier. Then I'm going to show some examples of how it responds to a frequency, and that'll be it. This is a simple block diagram of our system. There's the blue, the input motor, which is the only variable we can control. We can control it as a percentage input, and it runs through in the output, the voltage that we measure. It's a lot easier to see here. Left to right, you can see the electric motor that we control the input of runs the generator. The generator has an output voltage. The bank of light bulbs here is more just a visual representation of what's actually going on, so that you can see, what the generator is doing, as opposed to just a line on the graph. Some of you have already seen this. This is the SSOC that Tim showed. Instead of being just a straight line like some systems, it's got at least 4 obvious, distinct regions, the top of which we consider to be our operating range, from about 70 to 85, but that's where we stop it. Obviously goes up to 100%. This is just an example of a step. Instead of just an immediate response where it jumps up to where we want it, you can see from the curve that it takes a minute to, well, not a minute literally, but it takes time to even out to where we want it to. And from this, you can use the fits, this fit 1, 2, and 3 to determine your gain, your time constant, your dead time. And the 4 of us did several different runs at several different inputs, and we came up with time constant differences. And if you remember the different regions on our SSOC, you can see there's really no correlation between the regions. The only thing that's the same for the time constants on all of them is the step up is higher than the step down. But other than that, there's no real relationship between the different regions. The dead time is even more varied. It's not the up is higher than the down. It's different every time, pretty much. But if you look at the actual values, they're so low that when you're measuring it in Excel, you're doing visual, and it's not as accurate as it could be, and that can affect some of what we're seeing there. This is the gain that we calculated, and except for the 0 to 50%, this one is a lot like time constant. The step up is higher than the step down. This is just an example of how the system responds to a frequency. And the blue being the input and the red being the output. And you can see a slight lag from the output, which is what we would want. This is a chart of several runs at different frequencies. This one was an input of 70% with a 8% step. From 0.03 hertz to 6, and the amplitude ratio drops as the frequency goes up, while the phase angle is increasing. From all that data, you can plot it on the Bode diagram, and you can get an accurate reading of your gain and several other factors. The thing that surprised me, which I shouldn't have, is the step here. It took a long time to go from the 0.03 hertz, and then once you get all the way to 2, the step there changes a lot. And that's all the progress we've made on the system so far.